All right, hello. This is the lecture for Wednesday, week two. Um, you may have heard that looks like remote instruction has been extended to at least the end of January. And I've also been given the flexibility to make the entire course online. Um, I'm leaning toward that at this point because my experience last quarter is I have to I have to offer a hybrid course, right? Some people are just going to have to take the whole thing online. And given the option, it seems like about 90% choose that option. Um, and then just trying to do like a hybrid course, major pain, especially if only a few people take advantage of it. So I will send a formal announcement when I'm 100% sure, but we're looking like it's going to be a remote class this quarter. I hope it doesn't disappoint anyone too much. I imagine you're pretty used to it at this point. And I just don't know. Like, it might come end of January and they're going to extend it for another month or whatever. So, rather have everything be predictable. So that will mean, again, I'll confirm this later. That'll mean all the exams and everything will be online too. I'll have to make some adjustments, right? So this lecture, um, the last two lectures were kind of crucial, right? That was building this model that we're going to use to analyze scientific episodes. And the bulk of like your first exam is going to be on that stuff. So this lecture and the next lecture um, is going to involve applying that model, right? So make sure that you understand the last two lectures. Um, this is more examples from history. Uh, I'm only going to cover two of the examples from the chapter because I did promise you a slightly shorter lecture today since the last one went a little bit long. And it gets a little repetitive, but I do encourage you to read the rest of them in the book. All right, so as I said, this chapter and this lecture is just examples, right, from history um, of scientific episodes, and we're going to apply our method of analysis to them. So why do that? I mean, part is just to practice, right? The best way to sort of understand this method is to try it over and over again, right? That's also the point of the exercises. Um, these cases were chosen by the authors also deliberately because they sort of like are examples of particular types, right, of scientific episodes that you'll probably encounter later on in the exercises and the exams and so on. Um, Even though I'm only going to cover a couple in this lecture, I highly recommend that you read the rest of the chapter. It's enjoyable if you have any interest in science or history of science at all. Um, and then having read all those examples, when you encounter a similar one, right? These are sort of analog models for other find. When you encounter them on an exam, you might be like, oh, yeah, this is like that one in the book. So I do recommend that you read the entire chapter. I think it's not too difficult. It's kind of interesting. All right. So the first of the two historical episodes that we're going to cover is the phases of Venus, Galileo, right, and his experiment that and the results of that was sort of deciding between the reigning, what we call the Ptolemaic model of the universe, or at least the solar system, and the new Copernican model. So, what are these two models? So, at the time, so Galileo, we're looking at right early 1600s, basically. Um, since the times of the Greeks, the primary model of the universe had been what we call the Ptolemaic, named after Ptolemy, right, a Greek astronomer. Um, he first published his model of the solar system in 140 CE or AD, uh, and the model was Earth, center of the universe, right, and then orbiting around the Earth, all the planets, the stars, the sun, the moon, etc. Um, I guess sort of a natural thing, right? If you're standing on the Earth and you're seeing the stars move through the heavens, your first guess might be, oh, everything's rotating around me. Um, Now, there was a competing model that had been proposed for Galileo's time by Copernicus, right, in the mid 1500s. And on that model, the sun was at the center of the universe. But most people at the time believed the Ptolemaic model, right, with the Earth at the center. So Galileo, uh, he was favoring the Copernican model, right? So some similarities here with our DNA story, right? the other sort of suggestions are out there, right? And everybody thought that it was proteins that were responsible for genes, but a few people thought about DNA, right? And Galileo's sort of in a similar situation. He knows this other theory is out there, and he's thinking maybe it's right. Um, so he came to believe it, right? The Ptolemaic model was all tied up with sort of religion and stuff, so it was not always wise uh, to buck the trend, right? You could be seen as a heretic, right? So he kind of kept it to himself that he believed this Copernican model. So in 1609, Galileo heard about this new invention, the telescope, closer look at heavenly bodies. So he heard about them. He built one for himself, right? Began to make much more detailed observations of right, the motions of the heavenly bodies. Um, it may have been one of Galileo's students that suggested this, but he came right to the idea of like how you could test the two models. The idea is this. On the Ptolemaic model, as you'll see here on the right, you've got the Earth, which is down at the bottom there. I think I've lost the label, or maybe my head is in front of it. That's the Earth down the bottom. And again, on the Ptolemaic model, we're in the center of the solar system, right? Sun over there, and in between Earth and the Sun is Venus, right? So this is everything's rotating around Earth. So on that model, now on the Ptolemaic model, this is a little weird. We don't have this in our current model. To make sense of the observations that they made, they had to add what they called epicycles, right? So not only did the planets and the stars rotate around the Earth, but they also had made little rotations within their rotation. That's what that little circle is in the bigger orbit for Venus. So this is what the Ptolemaic model is, and Copernicus or his student were both deduced from that model that we should never see Venus fully illuminated, right? Because it will always be between us and the sun, right? So the sun will only ever hit one side of it as viewed from Earth. That makes sense. Whereas on the Copernican model, which, and we'll see on the next slide, a picture of that, but on the Copernican model, because the sun is at the center, right, and the Venus is between the Earth and the sun, there will be times, namely when Venus is on the other side of the sun of the Earth, that we will see Venus fully illuminated. Right? So these are different predictions, right, that have been deduced from these two models. Now, you can't see this from the naked eye, right? Whether Venus is in shadow. It's like the phases of the moon, right? With a telescope, you should be able to see it, right? So in 1610, Galileo actually observes this, right? So he sees Venus go through these phases, just like you see with the moon. It goes from dark to a crescent, fully illuminated, back to crescent, back to dark. Right. So here is the picture of the Copernican model with the sun at the center, and you see the Earth down there at the bottom, um, slightly cut off by me, and then Venus on the other side, and this is the configuration where you see Venus fully illuminated, right, as seen from Earth, at least, right? And then you can see further down around on the side, when Venus is closer to Earth, um, it will be partially illuminated, and you can see that it would go through different phases, right, through its orbit, as seen from Earth. So, sounds like Galileo was right. So let's apply our analysis. Okay, so step one, what is the real world object that's at issue? Well, these are the heavenly bodies near Earth, right? How are they arranged? How they move relative to one another? Right? So these are actual things in space, right? We want to know how they're arranged. So that's the real world. Step two, model. Model's been pretty explicit in the way this was described, right? We've got the Ptolemaic model, in which sun, moon, planets, stars all revolve around Earth. Then we've got the Copernican model with the Earth and the other planets revolving around the sun at the center. Right? Now, of course, the stars do not revolve around the sun, right? But at the very least, as far as the sun, moon, and planets. Right? Okay, so what are the predictions of these two models? Again, the prediction includes just using logic, right, derived from the models, and then also an experimental setup. Here, the experimental setup is a telescope, right, that helps you to just view, right, at a higher resolution planets. And the predictions of the two models are that Ptolemaic model, um, telescope, so that you can see Venus closer, you will never see like a full Venus, right, like a full moon. It will always be partially occluded. Um, And on the Copernican model, it predicts there'll be a series of phases, right? So if you zoom on Venus, very much like the moon, which we can see right without a telescope, you'll see it go through phases, one of which is full illumination. So those are the predictions of the two models. So what is the data? Well, the data was derived, right, again, from an interaction with the world, in this case, viewing Venus itself through a telescope. Um, Indeed, we saw the full series of phases, one of which is full illumination. So our analysis. Step 5, is there negative evidence? The data do disagree with Ptolemaic predictions. Negative evidence. There is evidence, right, that the Ptolemaic model does not fit the world, and there is agreement with the Copernican model. This is looking like a crucial experiment, right, where we have two models and we have a single experiment that's deciding between the two. So since we have some positive evidence vis-a-vis the Copernican model, now we move on to step 6. So we do have agreement between the data and the model, and the question now is, uh, would the data be likely if the model were false? Or again, in other words, another plausible model? And again, it's not your job to try to construct some other model for the universe. Probably, maybe you could. But for our purposes, was another model mentioned? No, they only talked about two models, right? The Ptolemaic one and the Copernican one. So again, it's just layperson consumers of science. Um, we're justified in saying that the data provide good support, positive evidence the Copernican model fits the universe. So, what happened, right? Galileo win a Nobel Prize. The Nobel Prize didn't exist yet, right? But was he lauded as a celebrity? No, unfortunately. Right? At the time, uh, many people were not convinced, right? They had not taken this course. They didn't know what to do with that data. Um, there were some legitimate, right, concerns. I mean, people wondered if maybe there were data was just sort of an artifact of the instrument, or in other words, the telescope itself, right, that was causing it, making it appear as though Venus was going through those phases. Right? So it's possible, right? Maybe there's dirt in the telescope. Maybe there's something about the way the mirrors and the lenses are arranged, right, that make it look like that. That's a possibility, right? Not crazy. Not something we can evaluate personally. We're not telescope experts, right? People also did wonder why Venus didn't appear to the naked eye to get bigger and smaller. So on the Copernican model, right, there's times when the Venus on the other side of the sun from us, and then times when Venus is between us and the sun. So that's a pretty wide discrepancy in distance, right? So why doesn't Venus seem to be getting bigger and smaller? Um, well, Galileo had an explanation for that, right? It just so happens that when Venus is farthest from Earth, that also happens to be when it is fully illuminated, right? So you're seeing more of Venus, so it's appearing larger than it otherwise would, right? When it's closer to us, you're seeing less of it, right? Because um, it's like crescent Venus, right? So uh, you end up sort of maybe by accident, it looks sort of uniform, right? That was Galileo's explanation. I don't know if there's a better one, to be honest. It might just be that it's when something is that far away that there's not that much of a difference, right, in how it looks. Um, Other people wondered how the Earth could be rotating around the sun at all. If it's going that fast, why don't we just fly off, right? Um, some of those are good reasonable questions that you might even ask now. Some of them now we wouldn't worry about, right? We don't worry about why people aren't flying off the Earth. If it's going at a constant velocity, right, that's not going to cause. Is only if the Earth were accelerating we would feel the G force. Okay, so it took 100 years before people started to slowly change. right? So a crucial experiment like this doesn't necessarily instantly mean that people are going to sort of believe it. But again, part of the point of this class is that hopefully you would have been one of the people to believe it, right? You've seen the models, you've seen the reports, and as best as you can tell, right, Galileo showed that the Copernican model is supported. I'll give you a moment to answer the attendance quiz. I assume we know procedure by now. I think on the last one, something on the form, I guess it was probably my fault. Um, but you weren't able to enter your PID. Okay, the form does give me your name, so the PID was sort of like an extra backstop in case there's any similarities in names or glitches. But I think this one should be normal. So yeah, put in your PID and then the letter of the quiz. So hopefully this is enough time to do that. Again, as always, you can pause if you need to. So I will move on. Okay, that was example one, right? We'll give you one more example, and again, I think we'll probably wrap up around 30 minutes or something like that. So this is Isaac Newton, right? So here we'll have an example of like a full theory. We won't get into too many of the details, right? But we talked about how a theory is sort of a group of models, like a family of models. Um, and Isaac Newton uh, proposed a very influential theory of mechanics that was sort of dominant for centuries, really, until Einstein. And even now, if you're dealing with stuff that's sort of relatively slow compared to the speed of light, right, and objects that are relatively small compared to like planets, Newtonian mechanics still does a pretty good job of the data. Okay, so Isaac Newton lived about a generation after Galileo, um, and he unified all these theories of the sort of the movements of terrestrial objects, right, like tables and chairs and balls, right, with objects in the solar system, right, a system, a theory that predicted the movements of all these different things. His model dominated until Einstein, and then, as I said, is still pretty useful now, right? Um, so interestingly, the objects in Newtonian models aren't tables and chairs and things like that. They're called bodies, and bodies essentially aren't actually like necessarily real objects in the world, right? But they do some property. They're sort of these abstractions, right? But they do share some important properties with things in the world uh, to a close enough degree that. So, here's some of the important properties that bodies have according to Newtonian mechanics. A body will have a position, right? So at any moment, a body is located at some point in space. Um, Bodies have velocities. So velocity is change in position per unit time, right? So notice he has sort of these primitive notions of position and time, and then you can define all these other things in terms of the others. So velocity is just change of position per unit time. Uh, Now velocity is different than speed. Velocity has a direction, right? So if you had two bodies, right, moving away from each other at 50 miles an hour, right, two cars that drive in opposite directions, they'd have the same speed but different velocities, right, because they're driving in different directions. Now acceleration, again, builds on velocity, so acceleration is change in velocity per unit time, right? So if you have position and time, you can get velocity, and with that, you can then get acceleration. So a body moving at a constant velocity, 50 miles an hour, has zero acceleration. Um, a body slowing down has negative acceleration. And again, some of this may be very familiar to you from school physics, right? But just a little brush up on this so that we can understand this scientific episode. Other important notions in Newtonian mechanics, mass, right? So mass is sort of an interesting thing. It's different than weight, right? So weight, I step on a scale, right? I weigh 170 pounds. Um, that's not my mass because if I were on the moon, I would weigh less. If I were on Jupiter, I would weigh more, right? So your weight is determined in part by your mass and also by sort of the mass of whatever bodies you happen to be near relative to considering your weight. So mass is a sort of intrinsic property, right, that you carry with you. I'll have the same mass on Earth and on the Moon and Jupiter and in space where I have zero weight, right, in the vacuum of space. All right, so um, it's a little fuzzy what mass is, right? And in fact, if you want to measure it, you have to use a scale or something, right? Or something else. It's kind of hard to measure mass directly, but it's sort of the quantity of matter, how much you have, right? Um, Momentum is another important concept. So momentum is defined as the product of mass times velocity, right? So if you have a mass of a certain amount times velocity, that'll be your momentum. A body standing still, no momentum because there's no velocity, right? So even if huge, right, a giant truck that's not moving has no momentum. Um, and force, so again, this is maybe more so than mass, is a bit of an abstract sort of concept. Um, and it's often a lot of these concepts are sort of interdefined holistically in this theory, right? Um, so if you want to know what mass is, you'd have to define it in terms of I have the equation over here on the right here, right? Mass times change in velocity over change in time. But basically, force is what makes bodies change their motion. So if you want to accelerate something, you need to apply a force. If you want to stop something, right, that's moving at a velocity, you need to apply a force. All right, given those basic concepts, now we can say sort of Newton's basic laws of motion. So the first law of motion is that if there is no force acting on a body, the momentum of the body will remain constant. Um, so that's so. For example, if a body is moving at a constant velocity, it's going to keep doing so indefinitely, unless some force acts on it. Now, this is sort of a revolution of the Newtonian mechanics. Sort of like, I think our default folk theory, right, is that right if you throw a ball, it doesn't just keep going forever, right? It kind of slows down and stops. Intuitive view is like, oh, I've sort of like I put my force into the ball, but then it sort of runs out. And Newtonian sort of that's sort of Aristotelian view, right? That things go down on their own. But Newton points out that no, actually, what's going on is like friction and gravity and things like that are actually forces acting on the baseball, right? So if you throw a baseball in space, it's going to keep going until it comes near some more massive object, right? Sort of force. Second law of motion: if there's a force acting on the body, that body will accelerate by an amount directly proportional to the strength of the force and inversely proportional to its mass. That just means that the more force you apply to a body, the greater the acceleration, um, and the more massive the object, the less acceleration you're going to get out of that same force, which should be intuitive, right? If I'm using all my strength to push a baseball, right, I'll get much more acceleration than if I'm using all of my strength to throw like a big medicine ball. Right? The third law of motion: if one body exerts a force on a second, then the second exerts a force on the first that is equal in strength, but in the opposite direction. So this is the famous dictum that you've probably heard: for every action, there's an equal and opposite reaction. And it's a little bit counterintuitive sometimes, but it makes sense, right? When you hit a pool ball with the cue ball, the way it works is right, the numbered ball rolls away and the cue stops, right? Why did the cue stop? Because the ball it hit exerted force, right, onto the cue. Um, and finally, the law of universal gravitation, right? So any two bodies will attract forces on each other that are directed along a line, connecting them, and these forces are proportional to the product of their masses divided by the square of the distance. So you've got two planets, right? They're going to exert force on each other, but if they're very far away, that force will be relatively small. The closer they are, the greater the force. Um, and how great that force is also going to be uh, determined by how massive these objects are. So again, as I said, right, Newton's model doesn't actually refer to any sort of actual objects. They're these idealized theoretical objects called bodies. They probably don't behave exactly like any real world object, but right, we can apply them to real world objects and get pretty close predictions. So again, this is just an example, right, of a fairly elaborate theoretical model, right? Not it uh, covers a lot of different areas, right? It covers any body moving anywhere, right? Planets in space, near the Earth. And it does a very impressive job predicting that behavior, which is why Newton is so famous. And kind of astonishing, right? What Newton, right, hundreds of years before we ever went into space, right? He predicted that the difference between mass and weight, right? Humans are massive objects, but they go into space and they are weightless, right? So there is a difference between mass and weight. So yeah, impressive work, right? Sort of modified, superseded eventually by Einstein, but nonetheless still influential. Um, Now notice we haven't really used any equations. I flashed some on the board, but in the book they don't use any equations. Um, that's fine, right? You could, right? You can use equations to describe a model, or you can just use words, right? The more complicated the model gets, the more useful mathematical symbols are. They're not necessary. All right, so on to Halley's Comet, right? So comets seem to appear in the sky at very irregular intervals and locations. There's been sort of like, because they're sort of so unusual, because since the beginning of recorded history, people have been carefully observing the heavens, right, and tracking the motions of the bodies. And these comets seem to appear out of nowhere, right? Everything is typically fairly regular, and you're very familiar with all the stars and everything, and all of a sudden this comet shows up and goes away. So these are notable events and have been noted again throughout history for hundreds of years. Um, so they seemed to beg for explanation, right? And Newton's model, if it's correct, ought to govern comets in just the same way it governs other celestial bodies, right? So that means there must be some sort of underlying regularity to their motion, right? They're going to move, right, because they are under the influence of forces, right? Gravitational force of nearby massive bodies. So Newton's theory allowed for different types of orbits, right? Elliptical orbits and parabolic orbits. So if a comet has an elliptical orbit, it's going to reappear in the sky regularly. Parabolic orbits will sort of loop around the sun and then shoot off far and away from the solar system and eventually come under the influence of other bodies, right? So it's not going to come back regularly, right? So Halley was actually a contemporary, a friend of Newton's. He wanted to investigate a particular comet that he had observed in 1682, and he combed through historical records for comets with similar orbits, right? So again, you can, when a comet appears, you're going to track its path through the sky, and then you can go back to historical records and see if anybody did a similar tracking and see if it lines up. And he did find one in 1606, another in 1530, with a relatively similar path, right? So we're the same comet, right? Then it must have an elliptical orbit, right? As we saw, the only kind of orbit that's going to have the comet coming back with regularity. And it looks like it would pass the Earth every 76 years. So we did some calculations, right? And determined that it ought to return in December 1758. And sure enough, it does. He's dead, but the comet does come back. So let's analyze this scientific episode, right? Step one, real world. What is the phenomenon under investigation? It's the path of a comet observed in 1682. Is it elliptical? Is it parabolic? Uh, is it predictable in any way? Right? Step two, the model. Well, the model is the Newtonian model for two bodies in an elliptical orbit. And the two bodies are the sun and the comet, right? So if the comet is in an elliptical orbit, right, then we can make certain predictions. Step 3 prediction was that the comet would return near the end of 1758, and this was derived from past observations, right, and again Newton's model that said, well, if if we have a body, right, that's in a certain relationship to another body, namely the comet and the sun, right, we can predict orbits, and if it's a certain type of orbit, then it will be regular. So, looking back and seeing the potential regularity, we can make a prediction about the next time it would be in our area. So, is there negative evidence? No, right? The data seem to agree with prediction. It came when he said it would come. Is there positive evidence? Uh, right? Well, it does seem to agree, right? The data does seem to agree with the prediction. Question is there an alternative model? Well, I mean, yeah, there's other things that could have happened, right? It could have been a different comet, just with the same orbit, right? Right, again, because not only did he see a comet at regular intervals, but it was a comet that traced a similar path across the sky, right? So for this to be sort of a coincidence or a different comet, uh, it's slightly less, or it's much less plausible that just sort of randomly a different comet would come exactly when he predicted it and trace the exact same path through the sky, right? So that seems very unlikely. So the data provides good evidence that the Newtonian model does in fact fit the behavior of comets. All right, so again, those are just two of the examples, just walked you through two of the examples. Text, uh, your homework exercise are due Wednesday night. And again, don't worry so much about getting them right. Uh, your TAs are going to be grading them, but only they're going to skim them and look to see that you made an honest effort, right, to answer these questions. I'm giving you a lot of exercises because, again, I think, first of all, it's an easy way for you to get points towards your grade, right? Put in the effort, but also it's important with this sort of class. You do have to practice this stuff a bit. You can't expect to just read the text and then move on the quiz. So, again, I'm trying to reward you for practicing it and helping yourself out on the quiz. Um, so the TAs, because I'm giving you so many exercises, nine different sets, try to keep it reasonable, right? 3 problems per set. Every week you've got more. So I can't expect the TAs to grade those in detail and give you comments, right? Discussion section is a good opportunity to ask questions if you had questions about these, but again, they are simply looking to see that you did them. Um, so yeah, do Wednesday night, 11:59 p.m. And I will not see you in person next week. Okay, that is an old slide, so sorry about that. I'll change that before I post the slides, so no one gets confused. Um, but yeah, I will expect an announcement if I decide that we're just going to go remote for the whole quarter, rather than sort of like waiting every couple weeks to see what the university decides. All right, thanks. That was it.